So now that we've talked about the structure and functionality of the client portion of the PrimeCheck app, let's take a look at the source code. And this source code is going to kind of show you the steps involved and how things are implemented, and it will also reveal some kind of cool things and also give you some things to be aware of, traps and pitfalls to be wary of when you use structured concurrency with virtual threads in the context of client-side concurrency. So as usual, you can find this code in the EX1 project in my WebMVC folder in my Live Lessons GitHub repository. So we're now going to turn our attention to the client portion of the implementation, and we're first going to talk about some of the classes we've got here. For example, here is PCClient parallel stream. This is what we looked at before, but just to kind of quickly go through it, this one's quasi-interesting because it's so easy to use parallel streams to do this code. There isn't much to think about. But in effect, what we're doing here is we have this test individual calls method, which has a list of prime candidates, and we're going to use the stream support.stream method to make ourselves either a parallel or a sequential stream. And then for each item in that stream, we're going to go ahead and call the checkIfPrime method on the proxy, saying we want to do this with a parallel stream, passing in the prime candidate, and then get the results back into a list. So that's how we did with the list. And then here's how we test the list call, much simpler, because all we do in this case is just forward to the proxy saying, this is the parallel stream strategy, here's the list of integers, and should I run it in parallel or not? So you kind of get a sense of what's going on here because we looked at the proxy earlier. This code works nicely, just out of the box, and it works fine because there's ultimately a thread pool, the common fork join pool, underlying the parallel stream. And so as a result, we're not going to have that many calls running concurrently because of the fact that we are bounded by the number of threads in the pool. Now, if we really wanted to be smart, and I probably should update this example to make this point, these checkIfPrime proxy calls are not CPU-bound operations. They're I/O-bound operations. Why are they I/O-bound operations? They're I/O-bound operations because they're actually making calls to the server, and that can block. So as a consequence, we're probably underutilizing the amount of available concurrency by using the common fork join pool out of the box. What we really should be doing is we should be combining this with this concept called a managed blocker. We've talked about that before, and that allows the common fork join pool to grow and expand as the computations are taking place if calls are blocking. So that would probably actually make this run a little faster. But I think it's still likely to be the case that, well, I'd actually have to play around with it to see if that's going to be an issue. But out of the box, without using managed blocker, we're not going to worry about other resources being overwhelmed because we're limiting the number of threads that are running concurrently. So keep that in the back of your mind. With that in the back of your mind, let's go take a look at the structured concurrency implementation. Now, the structured concurrency implementation, of course, is going to have a proxy, just like the parallel streams version did. It's going to be auto-wired, just like the parallel streams version did. But it's going to have to be written a little bit differently. So here, for the test individual calls method, we're going to call two different methods depending on whether the flag for parallel is true or false. So if it's true, we call test individual calls parallel, and if it's false, we call test individual calls sequential. So those are the two different options we've got here. So let's go take a look at the one that does things sequentially first. That one's really quite simple. And you can see all we do here, we don't really even use structured concurrency at all. There's no point since we're doing it all in one thread. And so we make ourselves a new array list of integers. Here's using good old Java 7 style syntax and semantics. We iterate through the list of prime candidates. We call the method checkIfPrime through the proxy, add the result we get back. It's not a future, it's just the result we get back to the list, which is just this array list of integer. And when we're done, we return the results. Very simple, very straightforward, very old school object-oriented Java. The downside, of course, is there's no concurrency. So let's take a look here at the concurrent model, and this will reveal a bunch of different things. So as you can see now, we're actually going to use the newfangled structured task scope shutdown on failure mechanism rather than what we did on the server side when we used the executor service mechanism. So what we're going to do now is we're going to have this try with resources block, and we're going to define ourselves a new scope, which is the structured task scope shutdown on failure instance. And then, just for fun, we're going to use streams, because why not? We're going to go ahead and convert the prime candidate list into a stream. And then for each element in the stream, we're going to go ahead and fork off a new task that will run in its own virtual thread. And what that will do, no surprise, is it's going to go ahead and check to see if the number's prime, this time using the structured concurrency parameter to indicate what method to run on the server. And so that will go off and do its thing. And then what's going to happen is we're going to end up with a stream of futures to integers. So stream of futures to integers. And so we're going to convert that into a list of futures to integers, which is what we have at this point. Now, at this stage, we're going to go ahead and use the barrier synchronizer. We're going to say scope.join. Remember, scope.join waits until either everybody's done successfully or someone failed. If everybody's done successfully, we have the results in hand. If somebody failed, then we're going to throw an exception using the throw if failed method. Notice how we were able to chain them together in a nice fluent interface style. And then the last thing we do is we do future to objects, where we take the results and we go ahead and convert that list of futures to integers into a list of integers. And that's what gets returned from this method. And if for some reason an exception occurs, we just return an empty list. Now, at first glance, this code looks fine. But the tricky part occurs, as I discovered to my chagrin when I first tested this out a couple months ago. If you have a lot of integers that you're testing for primality, the virtual thread mechanism scales quite nicely. I could have 100,000 integers in my list, and those would go off, and there'd be 100,000 virtual threads on the client. No problem, everything's happy. But I kept noticing I was getting this exception when I would run for anything more than just a couple hundred of these integers. And of course, the problem was that each of those calls, because it was in its own thread and there was no thread pool, was trying to open its own connection to the server. And connections are a precious resource. And so that wasn't working, so it was blowing up. So I scratched my head a second and I said, oh yes, of course, the solution to this is to do the following. So what I did, and this is really cool, this again demonstrates the power of Spring, where you can configure things in without having to write a lot of extra code. So what I did is I went into my client bean. I should really call this client bean as opposed to components, because it's a client bean. So I have a client bean here, and the client bean had a method called getRestTemplate, and that's how the client got the REST template to talk to the server. And what I did before was I just made a new REST template and told it what port number the server was listening on. That was it. When I realized I was running out of connections, running out of slots on the client, I said, aha, there's an easy way to fix this. So of course, what do you do when you run into a problem these days and you're trying to program? You go to Stack Overflow, right? So I looked up in Stack Overflow and said, how do I do a connection pool that will be sort of thread agnostic in Spring? And they said, oh, here's how you do it. So what I do is I have an environment variable, which I'll show you in a second, and if it's set, it'll tell me to use pool connections as opposed to non-pooling. And if I do that, then I do all this gobbledygook, which is what I got straight out of Stack Overflow. And basically what it does is it's making a connection pool with no more than 100 connections open at any given point in time, which is below the threshold that will cause problems with running out of sockets. And there's some other configuration flags and so on. So we go ahead and make this thing. You make that particular implementation. Then you make a REST template using the request factory that makes the connection pool. So if the connection pool is enabled, you make a REST template that has a connection pool associated with it. In any case, you then set the server base URL in the URI template handler so it knows how to connect to the right server, and you return that template. And what's cool about that is then any place where I need to get access to the REST template, like here in my proxy class, where you can see I have a auto-wired REST template, that will automatically go and use the bean that creates a REST template, which now will interpose transparently a connection pool. So the connection pool enabled me to be able to deal with the fact I could have hundreds of thousands of threads, but a much smaller number of connections open by having a pool of connections. So just a neat thing to know, and also kind of cool how Spring allows you to transparently inject that implementation into this code without having to perturb the implementation of the client. So now, armed with that knowledge, we can come and finish off our discussion of the client. So here's the test list calls stuff. There's no need to do anything. The concurrency in this case is all done by the server. So we just say, I'm the structured concurrency guy. Do you want me to run in parallel or not? And then the last piece of the puzzle is the proxy. As we saw, we can inject in the REST template using auto-wired and dependency injection. And then down here is the actual implementation of the checkIfPrime proxy method and the checkIfPrimeList proxy method. And of course, those are both implemented correctly because this code has to compile, unlike the slides in the previous discussion, previous lesson. So this basically just shows how you encode the parameters. Now, a couple other things to note. If you are really super cool, you will be using a proxy generator like Retrofit that will create the proxies for you automatically. We don't do that here, but you could do that. I want you to see how you write proxies, but that's another technique. And we'll look at some examples later in the class that use Retrofit and demonstrate how proxies can be generated automatically from descriptions of what the type signatures are for your interfaces that are running on your controller. Okay, so that's the end of the walkthrough of the client code.